Calculating Ka or Kb when pH or pOH is given. To examine this, let's first look at example number 3. A 0.25 molar solution of carbonic acid was found to have a pH of 3.48. What is the Ka for the carbonic acid? To approach this question, we first need to write out a Bronsted-Lowry acid-base reaction. Carbonic acid is H2CO3 aqueous. This can be identified as a weak acid, so we must react this with water, which will act as the base. Neither of these are strong, so we'll use an equilibrium arrow, and this will create HCO3 negative and H3O positive. Let me try that again. And H3O positive. Okay, so again, the carbonic acid acted as the acid, water acted as the base in the Bronsted-Lowry acid-base reaction. I know that this acts as the acid since it asked me to calculate the Ka. Remember that eventually we will need to write out an equilibrium expression, and liquids are not included in the equilibrium expression, so we will not include it in our ice table. We will set up our ice table. I know that I need an ice table because it told me that I had a 0.25 molar solution of carbonic acid, but it did not tell me that that was at equilibrium. So I go ahead and I assume that that would therefore be the initial concentration, 0.25. We always start off with no reactants. We lose reactants, we gain products. All of these have the coefficient of 1. And in the equilibrium line, we combine the initial and the change. Okay. Once you have your ice table set up, you go back for the extra piece of information, and we were told that this solution has a pH of 3.48. So from that, you ask yourself, what information can I get from pH? And recall from the beginning of this unit that we can get H3O positive, or the concentration of the hydronium ion, which is equal to 10 to the negative pH, or the negative antilog. That would be 10 to the negative 3.48. You can plug that in on your calculator to make sure that you can use your calculator and you can follow along with me. Notice that the pH has 2 decimal places, so our concentration will have to have 2 significant figures. So it will be 3.3 times 10 to the negative 4, and we'll include the units moles per liter. Again, this is the concentration of the hydronium ion. So now it becomes a question just like example 1 and example 2 from the last video, except instead of explicitly stating the equilibrium concentration of one of the species that we are looking at, they're now telling us the pH, and we have to take one extra step to determine what that concentration is. So we go back to our ice table and we ask ourselves, well, what did we say was the equilibrium concentration of the hydronium ion? And notice we find the hydronium ion, we find the equilibrium line, and we said that this was equal to X. So we have now found the value of X. From there we can find the other equilibrium concentrations. So I know that HCO3 negative at equilibrium we said was equal to X. So that's 3.3 times 10 to the negative 4 molar. And carbonic acid, H2CO3 at equilibrium, is 0.25 minus X, which is 3.3 times 10 to the negative 4. To the appropriate number of significant figures, that is not large enough to change the answer. So it's still 0.25. Fix that up there. Now that we have all of the equilibrium concentrations, we can write out our Ka expression, which is products over reactants raised to the power of their coefficient. And we can plug in what the equilibrium concentrations now are. We have 3.3 times 10 to the negative 4 molar times 3.3 times 10 to the negative 4 molar. Or you can simply write that as 3.3 times 10 to the negative 4 squared over 0.25 molar. These molars will cancel out, and we will get a final answer to the appropriate number of significant figures, 4.4 times 10 to the negative 7 molar or moles per liter. Example 4. The pOH of a 0.157 molar solution of sodium propanoate, as shown, is found to be 4.96. Calculate Kb for the propanoate ion. So we've been told that we have sodium propanoate, NaC2H5COO. And hopefully at this point there's a red flag that's going off. And hopefully, at this point, you now see that sodium propanoate is an ionic compound. It contains a metal, Na, with nonmetals. And we know that ionic compounds in solution dissociate into their component ions. Or you could have realized that we have a metal attached, and metals have no acidic or basic properties, so we need to get rid of that in step number 1. Okay, so any question we have that involves an ionic compound, anything with a metal, we need to get rid of that metal. It has no acidic or basic properties, so it's kind of useless to us in this question. So what we're going to write out when we write out a Bronsted-Lowry acid-base reaction is we're actually going to use C2H5COO negative, which is the propanoate ion, which is why the question asks for us to calculate the Kb for the propanoate ion and not calculate the Kb for sodium propanoate. The propanoate ion is weak, therefore we do need to react this with water. We need to have something there for the acid-base reaction. It is not strong, so we're going to use our equilibrium arrows. Okay. Looking at the propanoate ion, you should realize that this would have to be a base. The hydrogen at the end, COO, and there's no H there, so that's been missing. So this is the conjugate base. Therefore, water will act as the acid, and it will donate a proton. That will give us C2H5COOH plus OH minus. And we did get hydroxide as you would predict, seeing as the question asked for us to calculate the Kb. We were told that we had a 0.157 molar solution. It did not say that this was at equilibrium. Therefore, we have to set up our ice table. Liquids are not included in our expression, so it will not be included in our ice table. We have a 0.157 molar solution. None of that, and none of that. You will notice that we were told that we had a 0.17 molar solution of sodium propanoate, but there is a 1-to-1 relationship between sodium propanoate and the propanoate ion, so I can go ahead and use the 1.57. We lose reactants, we gain products. They all have a coefficient of 1, and the equilibrium line is just the first two put together. Once you have your ice table set up, you have to go back to the question for the extra piece of information. And in this one, we've been told that the pOH is 4.96. So you ask yourself, well, what can I find with pOH? And with the pOH, you can find the hydroxide ion concentration. It's 10 to the negative pOH. So this is 10 to the negative 4.96. Notice that the pOH has 2 decimal places, so our concentration will have 2 significant figures. 1.1 times 10 to the negative 5 molar. This is the equilibrium concentration of the hydroxide ion. We now ask ourselves in our ice table, what did we say was the equilibrium concentration of the hydroxide ion? And we said that that was X. So we have now found a value for X. Once you find a value of X, you can now plug in the X into the equilibrium concentrations from your ice table to find the equilibrium concentrations of the other species that are present here. The concentration of C2H5COOH at equilibrium is X, which we have found to be 1.1 times 10 to the negative 5 moles per liter. The propanoate ion, we said at equilibrium was 0.157 minus X. We plug that in on our calculator, and with significant figures, it's not big enough to make a difference, and it's still 0.157 molar. We can now write out what our Kb expression would be, not Ka. Okay, this is for a base since we have hydroxide. This is C2H5COOH times OH minus all over C2H5COO negative. We plug in our values, 1.1 times 10 to the negative 5 molar times 1.1 times 10 to the negative 5 molar, all over 0.157 molar. One of these moles per liter cancels out. And to the appropriate number of significant figures, we have 7.7 times 10 to the negative 10 molar. Again, that's Kb. If you turn over the page, you will now see example number 5 and example number 6, which are very similar to the first two examples that I've went through. I strongly encourage that at this point in the video, you just put this on pause and take a few moments with your calculator and go through example 5 and go through example 6 on your own. If you can get to the same final answer after you start the video again, I would feel very confident personally that I'm understanding the concept so far. Otherwise, still go through the examples, see how far you can get with it, and put a star when you get stuck. That way you can then identify to your teacher that you're having trouble up until this point and can get some clarity on that.